So today to talk about the equations of motion in the cylindrical coordinate system. But before that, let's just start with polar coordinate system. Then we can extend the same concept to include the vertical component, which is a z component. So assume that we have a particle that is moving following certain path, and at some time the particle is located, let's say here. So this is the position of the particle at any time t. So you can put here position of the particle at time t. So now, of course, this is what we call path. Now the position of the particle, it has to be done with respect to some reference. So assume our reference is O, which is this. Now we can locate the particle's position with respect to this reference, and this is what we will call R. This is the position of the particle, and we can also define the angle theta, with respect to the horizontal reference. So now that we have a particle that is moving in two-dimensional plane, now we can define two axes, the radial axis and the transverse axis. So the radius axis actually extends the position axis, so we can just put like this, something like this. So this would be the radial axis, so we can put here, we just change the color of the axis. So this will be the R axis. Let's change the color. This would be R, or the radial axis. Now perpendicular to this axis is the transverse axis. Okay, is the transverse axis. So it has to be perpendicular. So this is theta, or the transverse axis. Now assume that the particle has a mass m and it is subjected to forces. So those forces can be in any direction. Okay, can be in any direction. So let's say those forces are all the forces. I mean, when we take the resultant, all the forces are in this direction. So we put here sum of all forces. Now in the polar coordinate system r theta, we can resolve these forces into two components: sum of the forces in the radial axis and sum of the forces in the transverse axis. That's not like this. So let me just change the color. Let's put blue. So these are the forces in the radial axis. These are the radial forces, and we have those forces in the transverse axis. Okay, so we can type here, can write sum of the forces in the radial axis, and these are some of the forces in the transverse axis. Now we can write now the equations of motion. So we have sum of the forces, all force applied to the mass is equal to the mass of the particle times the acceleration. So sum of the forces is equal to the mass times acceleration. Now In terms of polar coordinate system, we have sum of the forces in the radial axis is equal to the mass times the acceleration in the radial axis or radial acceleration, and sum of the forces in the transverse direction is equal to the mass times the transverse acceleration. Now if we extend to a cylindrical coordinate system, we should add the third equation, sum of the force in the z or z direction is equal to the mass times the acceleration in the z direction. Now if you recall, the accelerations AR, A theta, AZ are as follows. So AR is equal to the second time derivative of the position minus R, the position, times the angular speed square. The transverse acceleration is equal to R times theta double dot, which is the angular acceleration, plus 2 times R dot theta dot, and AZ is the second derivative of the z component of the position. Let's treat the case of the existence of tangential and normal forces, and we are still going to use the cylindrical coordinate system, polar coordinate system in this case. And of course, you will need to resolve those forces, normal and tangential forces, into the radial and transverse axis. So let's represent now the radial forces, the radial axis. Sorry, the radial axis. So assume this is your radial axis. And this will be perpendicular to the radial axis is the transverse axis, okay? So this will be transverse axis, this will be the radial axis. We are assuming that this is our origin, okay? Now, you will need an angle. Let's call this angle psi. And this psi will allow you to resolve the friction force into two components. One component on the radial axis. So let's call this angle FFR, and another component on the transverse axis, and let's call this component FF theta. Of course, this psi is also this angle that extends between n and the normal force and the transverse axis. So psi is given as the tan inverse of the position over the derivative of the position with respect to theta. This is very important relationship, and it is very useful whenever you are using cylindrical coordinate system, but you have some tangential or normal force or both. So let's take an example, practical example, and see how we apply the formula. So let's assume R a path defined by R is equal to 5 cosine theta. it is in meters, and theta is given as, let's say, 3t, and it is in radians, and t in seconds. And we want to calculate psi at time t is equal to 2 seconds. Okay? So we know that psi is equal to the tan inverse of r divided by the derivative of r with respect to theta at t is equal to 2 seconds. So to solve this exercise, we need to calculate first theta. So theta we have is equal to 3t, and at t is equal to 2 seconds, theta is equal to 3 times 2, which gives me 6 radians. R is equal to 5 cosine theta, and at t is equal to 2 seconds, R is equal to 5 cosine 6 radians. So this should give me cosine 6 times 5 gives me 4.8 meters. Now we differentiate R with respect to theta, and we get minus 5 sine theta. And this, when t is equal to 2 seconds, gives me dr over d theta at t is equal to 2 seconds is equal to minus 5 sine 6, and this gives me minus 1 or plus 1 point, almost 1.4. Okay, now we can calculate psi, and it is equal to the tan inverse of r over dr over d theta, and gives me tan inverse r, we have it 4.8 divided by dr over d theta, and it is equal to 1.4. So we have tan inverse of 4.8 divided by 1.4, and gives me almost 1.29 radians. Okay. So in the next lecture, we will solve problems related to kinetics where we use the cylindrical coordinate system. Okay, so see you later.